You ever catch yourself using the words electric and electronic like they're the same thing? Yeah, most of us do. An electric guitar, an electronic keyboard. But in the world of technology, those two words are worlds apart. One is all about raw power, and the other is about pure intelligence. So let's dive in and uncover the secret ingredient that really truly powers our modern world.
Okay, picture this. Your whole production line just grinds to a halt. Something's broken. But what? Is it the huge motor that was supposed to be moving the conveyor belt? Or is it that teeny tiny sensor that was supposed to tell the motor when to stop? Getting that diagnosis wrong could cost a fortune in downtime. So the real question you have to ask is, did the machine's muscle fail or did its brain?
And that, right there, is the key analogy for today. Just think of electric devices as the muscle. They do all the heavy lifting, the moving, the heating, the lighting. Electronic devices, on the other hand, they're the brain. They're all about processing information, making decisions, and telling the muscle what to do. One is the brawn, the other is the intelligence.
All right, first up, let's really break down these roles. We're going to get super clear on what puts a device in the muscle camp versus the brain camp. So, electric devices are basically the straightforward workhorses of the world. Their whole job is to take electrical energy and turn it into some other kind of raw power. We're talking about the motion of a motor, the intense heat from an industrial furnace, or the blinding light of a stadium lamp. These things are built for pure strength endurance, not for thinking.
Now, electronic devices? Totally different story. They are all about information. They don't just use power, they manipulate it in these tiny, super precise ways to handle signals and follow logic. A sensor doesn't actually move anything, it just collects data. A control board doesn't heat anything up, it decides when the heater should turn on based on that data. It's the command and control center.
Okay, so let's build on that and put these two head to head. We'll look at what they're made of, how they use power, and what really separates them at the most fundamental level. And you can literally see the difference right here. On the left, for the electric muscle, you've got these thick, heavy bundles of copper wire built for brute force. But on the right, for the electronic brain, it's all about precision. We're talking delicate microchips and complex circuit boards designed to manage information, not just raw power. And yeah, their appetite for power is completely different. Electric devices are absolute power hogs, running on high-voltage alternating current, or AC, the stuff that comes out of a wall socket. Electronic brains, though, they just sip power. They need that super stable one-way flow of direct current, or DC, like from a battery, to protect all their sensitive little logic circuits.
So how in the world can the brain be so smart while using hardly any power? Well, the secret is in a very special class of materials. We're now going to zoom way in on the magic ingredient that makes all of this possible, the semiconductor. A semiconductor, like silicon, is just a fascinating material. It's not a great conductor, like copper is, but it's not a great insulator, like rubber, either. It lives right in that sweet spot in the middle. And that in-between property is its superpower, because it means we can precisely control it to act more like a conductor, or more like an insulator. But here's the twist. A pure semiconductor, all by itself, isn't actually that useful. The real magic happens when we intentionally add tiny, calculated amounts of impurities into its crystal structure. This process has a great name, it's called doping, and it lets us completely change the electrical properties of the material. Doping gives us two different flavors of semiconductor. If we add an impurity that brings extra electrons to the party, we create what's called N-type material. N is for negative because of all those free electrons floating around. But if we use an impurity that's missing an electron, we create P-type material. This leaves a little hole, a space where an electron should be, and because it's missing that negative electron, the hole acts just like a positive charge. So, we've got two special materials. One has extra electrons, the other has these electron-sized holes. What do you think happens when we bring them together? Well, this is the aha moment. This is where we create the single most fundamental building block of all electronics, a one-way gate for electricity. The instant the P-type and N-type materials touch, physics just takes over. Those extra electrons from the N side naturally spill across the boundary to fill up the nearby holes on the P side. This first little migration is everything. As they cross over and find a hole, they basically neutralize each other right there at the junction. This creates a super thin layer right at the boundary, a layer that's now depleted of any mobile charges. No free electrons, no holes. This zone is called the depletion region, and it acts like a little barrier, stopping any more electrons from just casually wandering across. Now, this depletion region isn't just empty space. It actually has an electric field across it. And this field creates a tiny voltage, which we call the barrier potential. For silicon, it's about 0.7 volts. The best way to think about it is like a small hill that electrons now have to climb to get from the N side over to the P side. And on their own, they just can't make it over. And this is the absolutely crucial part. We can control the flow. By applying an outside voltage, a process called biasing, we can either give the charges a push to get them over that hill, or we can make the hill even steeper. This gives us two modes, forward bias and reverse bias.
So in forward bias, we hook up a positive voltage to the P side and a negative voltage to the N side. This literally pushes the holes and electrons toward the junction, which shrinks that depletion region. As soon as our voltage gets past that 0.7 volt barrier, the hill flattens out, and bam, current flows freely. The gate is wide open. But if we flip the battery around, we get the exact opposite effect, reverse bias. Now, we're pulling the charges away from the junction, which makes the depletion region even wider. That small hill just became a mountain, and basically no current can get across. The gate is slammed shut. Okay, so we've just created a microscopic one-way gate for electricity. Let's zoom back out and see how this one simple, elegant component is the foundation for every single smart gadget you have ever used. This little device we've just built, this PN junction, is called a diode. And its entire purpose, its whole reason for being, can be summed up right here. It acts like a one-way switch for current. It lets electricity flow in one direction, but it blocks it from flowing in the other. That's it. And this is where it all clicks together. This simple ability to say yes to current or no to current. What is that? That's a binary decision. That's a 1 or a 0. This is the simplest, most fundamental piece of electronic logic. It's the atom of information processing. And from this one principle, everything else is built. You can stack these junctions together to create a transistor, which is an electronic switch. You can then put millions or even billions of those transistors onto a tiny slice of silicon, and you have a microchip, the brain of your computer. It all comes back to this one beautiful little piece of physics. You know, we started this whole thing by separating raw muscle from intelligent brain. And what we found is that the brain is just built from countless tiny one-way gates that can each make a simple yes or no decision. So think about it. If one of those gates can do that, what happens when you put a billion of them together on a chip the size of your fingernail? Well, you get the modern